it relates to our assignment, and it's okay to make mistakes here. We welcome mistakes all the time because this is where we learn, right? So it's good to be making mistakes where we learn. So let's go ahead and look at, excellent, I'm getting some more participation up there. Beautiful, beautiful, loving it from people. Here we go. So let's go ahead and talk about this. So looking at our problem here, it says a blue whale. Okay, a blue whale are the largest and loudest. This is going to be a information that we're going to need. Loudest animal. They have very low-pitched voices. I'm going to take this information and highlight that because that's an important piece of information. Based on this, circle the best wave. So let's go ahead and recall for a moment. So amplitude. Remember what amplitude was. Amplitude, of course, is the height of the wave related to its energy or loudness. So remember that equilibrium that goes across that wave pattern. From the equilibrium to the crest, the very top bump there, that's going to be a measurement that we're going to look at. The smaller the amplitude, the quieter. The higher the amplitude, the louder we are. So the bigger the amplitude we get, the louder we get. I'm probably like this big in my amplitude here. And obviously, let's go ahead and take a look at frequency. Remember, we can recall what frequency was. It's the total waves per cycle related to pitch. So the longer the cycle, the longer the wave cycle is, again, low frequency is going to be low voices, very deep voices, usually men's voices. So, and then obviously a higher frequency, more wavelengths, it's going to be a higher pitched voice, very like a woman's voice, okay? Now, obviously people are different, humans are different, it goes vice versa, but just kind of give you that idea. Low voice is going to be low frequency, high voice is going to be a very high frequency. So, with this being said, let's take a look at what we just highlighted. So if a blue whale has a loud, is the loudest animal, obviously we're going to have a big amplitude, large amplitude. And now if the blue whale has a low-pitched voice, a very deep voice, then we're going to have a low frequency. And yes, I do agree with you. It is a large amplitude, low frequency. Excellent job. Digital high five, yes. So let's go ahead and look at our content question. So what is an instrument in the song that you choose from your project? Would you want to play or learn that instrument? And so we're looking at here the piano, and I'm taking lessons for. Awesome job. I love it. Who is this? Regine, that is so cool. Again, I didn't take piano. I don't know what my mom and dad were thinking. I don't know. Drums sound so cool, Brittany, or that was Mrs. Larkin. Bowen's playing drums. I don't know if I allow my sons to play drums in the house. I don't know. Daniel, I see you played the trumpet in 8th grade. That is so cool. I would want to learn how to use any of the instruments used to make the song. I just chose because I just want to. That's pretty cool, Sally. Like I said, I think it's so cool that somebody learns an instrument, any kind of instrument. Like I told the other classes, my brother is a self-taught bass guitarist, and he just learned, he played piano, learned how to read music, and just taught himself how to play a bass guitar. Now he's really good in the band. Me, on the other hand, I think I missed that because I was always in the dance studio, so I never played an instrument, so I wish I did. All right, let's go ahead and continue on. Now, obviously, we're in science class, but, you know, we're not in biology, but we're in physical science, and we're going to give you the fun facts about blue whales. Look at these fun facts. They are the largest animals ever recorded to live on Earth. Can you believe that? They can measure up to 100 feet long. That is the length of 3 school buses, the big school buses, yeah, and weighs about 441,000 pounds. Can you believe that? Yeah, no problem. You know what, I'm going to turn off my camera. Maybe that will help out there. Thank you, Mrs. Larkin. I don't want to sound like a chipmunk. We're talking about whales, not chipmunks here. All right, so their tongue weighs as much as an elephant. Can you imagine if they were like a dog licking you? You'd just fall over. My goodness gracious. They are the loudest animals on the planet, and they live about 80 to 90 years, almost like a human wavelength. Yeah, those crazy big tongues. I would be so scared to have that whale licking me. So just kind of a review here. A large amplitude obviously makes a loud sound, low frequency, low pitch, deep voice. But whale frequencies range about 10 to 40 hertz. Humans can't even hear below a 20 hertz. And like if you're old like me, I can't even hear below 40 hertz. That's terrible. But you know, hey, that's okay. blue whales, what we want you to get out of this is that blue whales are super awesome, and that they're super cool, and that their voices are extremely loud. That's why you can hear them from miles and miles away, and they're very, very deep. Obviously, we know that sound travels faster in water. All right, here we go. So our Class Connect sessions are recorded, distributed for learning purposes. Please do not put any personal information or information of others into the chat box for your protection and the protection of others. Always be respectful, and always, always participate here often and well. And I know you all do. So today is day 37 of our 60-day adventure together. It is the top of the week at Monday, October 12th, and today we're going to do our wave calculations, part 2. We're going to do this all through our Unit 4 projects and with our 4F attendance discussion. Public service announcement, make sure you're staying until the end of class to get that attendance, because it is super important that you do, and to get full attendance credit that you answer the question that we ask. So here we go. As we are chugging along on Unit 4, we're going to be talking about today calculating the speed of a wave using wavelength and period, or wavelength and frequency, and determine an unknown variable using the speed equaling wavelength times frequency equation. Now, you might see this weird little h. That's actually called a Greek, or a lambda, and we're going to talk a little bit about that. It is a Greek letter. So, yep, there it is. So it's a lambda, so that is going to equal our wavelength. Okay, you're going to see that sign a lot. You're going to see that symbol a lot, but that is going to equal wavelength, but we'll talk about that in a little bit. And we're going to demonstrate this all by completing slides 14 through 17 in our Unit 4 project. So here we go.
All right, everyone, we know the drill. We need to go ahead and get our projects opened and ready to go and copy the newest slides. Oh, I got a green check already. Oh my goodness, Andres, you are so on top of it. All right, so you have your 2 links here. If you've already started, remember, go ahead and find your original in the files right here, and then go ahead and open up the teacher version and copy the 2 newest slides, which we'll show you in a moment. Those will be slides 16 and 17. If you have not yet started, don't forget that you can get the clean template right down here. So this 3rd link is for you. If for some reason you've not been with us for all of Unit 4, then you are welcome to go ahead and just start the project right now. Make sure you get that template. And don't forget, if you try to open up any of the templates and they don't work and they say that you need to ask for access, please don't ask for access, because then it emails me 1,000 times with your requests for access. All you need to do is make sure that you have a real Google account. Remember, your school account is not a real Google account. You do need to manually sign up for a real one, and that link is right down here for you. If you would prefer to wait until the end of the project to copy all of the slides, and instead you are going to take pictures, screenshots, or writing down the answers in a notebook, then still give us green checks to let us know that you are ready to do that. I'm going to go ahead and share this with you real quick on the board on how to do this. So again, if you have opened up the first link, sorry, you can't see my board, can you? Let's try that again. I always forget that I need to do it differently with you all. All right, so let's take a look here. Perfect. All right, so taking a look here, remember this is where you find your files. So here is my example student version. Yeah, you can definitely use your mom's Google account. That's totally fine. You can use any Google account as long as it's a real Google account. So this is my student example right here, and you can see my student example does not have the most recent slides. Right here, this was the 2nd link. This is the teacher version. This is the version that you cannot edit, which is how you know it's the teacher version. Remember, go ahead and click on slide 16 and 17. If you want to click both of them at the same time to copy them at the same time and make your life easier, you can press Control and click both of them at the same time. Remember, CTRL, that is Control on your keyboard. Then go ahead and right-click on them and click, if my computer will let me. Go ahead and click copy. Again, if for some reason that's not working, remember the shortcut that Google will use is Control and C at the same time. So press Control and C at the same time. So go ahead, click copy or Control and C. Go back to your student version, click on the very last slide, which is currently slide 15. Make sure you're caught up on all the slides and that you've been copying them as we've been going through Unit 4. Again, right click and click paste. Again, that shortcut is also Control and V. So paste, Control V. into your student version, and there you go. You have the two most recent slides. All right, so slide 16 is 3 problems that we will be doing together. So these are the notes that you will complete. And then slide 17, you'll need to be able to do on your own based on our notes. So you'll do some examples with us. And then slide number 17, you need to be able to apply to your own project. And we will give those directions to you at the end of class. So let's go ahead and jump into it. Again, if for some reason you were having issues seeing my directions, go ahead and click on slide 16 and 17. You can press Control to select both of them. Right click and click Copy, or Control C is the alternative. Once you do that, that's from the teacher version. Once you do that from the teacher version, go to your student copy. Right click on the last slide, that's currently slide 15, and click Paste, or Control V, Paste. I need green checks all around to let me know that you are ready for that. I'm going to go ahead and give you 30 seconds. Again, if you are going to just take pictures, screenshots, or write down the answers, that's totally fine, but I still need your green checks. If we don't hear from you, we'll go ahead and check in with you in the check-in room. Go, go, go. All right, waiting on green checks from Alec, from Haley, Jose, Kalia, Luis, Matthew, Ricardo, and Timothy. Green checks, everybody. Daniel, let us know if you're still having issues. We can always jump into a workroom with you and help you out. So again, Alec, 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 Haley, Haley, Haley. Waiting on, let's see here, Luis, 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 Matthew, Matthew, Ricardo, Timothy, Ricardo, Timothy. Looking good. Again, even if you're kind of getting caught up, it's still good to take pictures. Even if you're focusing on getting caught up in other projects, still make sure you're taking pictures. That way it's easy to get caught up on this one too. I know there's a couple of you I've been working with individually. Still make sure you're taking pictures. Looking good. All right, everyone, let's go ahead and get started up here. So let's go ahead and do a brainstorm based on some recent news, which is pretty cool in my opinion. So on Friday, so literally just a couple days ago, October 9th, physicists came out with a new article that proposed a fastest, like maximum speed of sound. So they proposed that the fastest sound can possibly move is 36,000 meters in a single second. 36,000 meters per second. Taking a look at all the speeds that we've kind of been working with in our class, that's way, way faster. Take a look, right? In air, remember we said that in air, sound can only move at about 330, 340 meters per second and is pretty slow in air. So this is a crazy, crazy fast speed right here. Now, currently the fastest known speed, right? So the fastest known speed is in diamond, and it's about half that. So it's about half of 36,000 meters per second. So still pretty fast, but definitely not as fast as this. So this is a proposal, this is a theory, and the theory is based on a medium, all right, that is also theoretical. So the medium on which these calculations are based is also theoretical, and that medium or material is solid metallic hydrogen. Now, tell me in the chat box, hydrogen, is that usually a solid, a liquid, or a gas? Everybody in the chat box, hydrogen, is that usually a solid, a liquid, or a gas? Go ahead, tell me in the chat box. Thank you. I see Caitlin, I see Regine, I see Greta, Sally, Andres, Alyssa, Jalen. Looks like we're all agreeing. Andres fixing your spelling. Yeah, hydrogen is going to usually be a gas. There are such things as liquid hydrogen. Liquid hydrogen is really cold and is used for some experiments as well, which is a lot of fun. But usually it exists as a gas. Now, solid hydrogen is really, really, really difficult to make, to the point that we have never made solid hydrogen on Earth. It is purely theoretical. We believe that it might occur inside of the center of some planets, because in order to make something solid, you either need to be real cold, or you need to have really high pressures, all right, like the center of a planet, okay? So that's pretty crazy to think about. So this is purely theoretical, but based on our data that we've been looking at in class, this hypothesis should actually make a lot of sense to us. So let's take a look at some of the charts that we've been looking at. So we have right here, we have the speed of sound with some gases, some liquids, and some solids. Tell me in the chat box, where does sound move faster? This is something that we've discussed several times, and if you don't remember, just go ahead and analyze the chart right here. Where does sound move fastest, in gases, liquids, or solids? Take a look at our graph over here. Where do you see it occurring the fastest? It does move faster underwater, but where does it move the absolute fastest on this graph? Yes, awesome. Good correction. Yeah, so in steel, which is a type of solid, so you can see lead, glass, and steel, all of which are solids, the speed is much, much faster. So that should make sense that whatever material we theoretically move the sound the fastest in should be solid, right? So that does make sense that they chose solid. Now, what I want you to think about next is take a look at some of these elements down here, and where in these elements does sound move the fastest? Even though these are gases, all right, where does sound move the fastest in these gases? Where does sound move the fastest in these gases? We're taking a look at our second chart right here. Excellent. I see Antoine. I see Lisa. Regina on top of it. Thank you, Sally. Make sure I'm getting some more people that I don't usually get participation from as well. Want to hear from everybody. Thank you, Caitlin. Thank you, Jadelyn. Looking good, getting lots of answers. Yes, Brisa, there you are. So wonder where you were, Brisa. Awesome, Daniel. Yes, so hydrogen is going to be the fastest for our gases, 1,270, which makes sense over here. So it does make sense that if you combine these two, the idea that hydrogen is the fastest element and that gaseous element, and that if we were to make it solid, then it could be real fast. Yeah, krypton is in fact a real element. It is a real element. It actually can glow much like neon can glow. So neon lights and krypton lights are both like neon looking lights. All right, so taking a look down here, the next thing I want you to think about is why. Take a look down here, take a look at the size of hydrogen. So this right here is hydrogen. Compare it to the size of the other elements on the periodic table. So you can see oxygen and carbon, which is what diamond is made of. You can see silicon and sodium, potassium and helium. Compare the size of hydrogen. What does hydrogen look like in terms of its size? What does hydrogen look like in terms of its size? It's an itty bitty baby. Yes. I like that. Sally, Caitlin, Antoine. Yes, it is the smallest. It is very tiny, very tiny. And in reality, we cannot see atoms. So it's actually even tinier than what you see on your screen. It's the tiniest atom. We are currently unable to see it. It's way too tiny. Okay, it's a little baby. All right, so it's very tiny. And what scientists have discovered over time is that smaller atoms, which have a better proportion between their protons, which are positive, and electrons, which are negative, actually can carry sound better. All right, so this is something that we'll go over next semester when we talk about chemistry, if you're with us in chemistry next semester. So don't worry if those are unfamiliar terms. Just know that the smaller an element is, the smaller an atom is, the better it is at carrying sound. So this again should make a lot of sense of why hydrogen is the key here. So hydrogen, if we can make it solid, would be the best at carrying sound. If you would like to take a look at that article later, I have it in the chat box for you. But it's not the actual research because even I would have a hard time reading the actual research. So it's just an article on the research. But there have been several articles, and I thought that this one explained it pretty well. Great job, everybody. Go ahead and in the chat box, give me a rainbow if you feel comfortable with this analysis. Again, we're taking a look at the speed of sound, and we're taking a look at analyzing some charts and applying that to real research. Real research. Great. All right, so let's go ahead and talk about how do we calculate the speed of sound. So the speed of sound is the rate at which you pass on sound from particle to particle in a medium. Remember, we've talked about how sound does need mediums, and sound passes that wave from particle to particle. Now, believe it or not, we already have an actual equation for speed, which is the speed of an object, and that is that distance divided by time. Oh, my video is lagging so much. All right, so distance, so the speed, right, V here stands for speed. Remember, it can stand for velocity or speed. Speed is going to be distance divided by time. However, when we apply this to a wave, we need to go ahead and use some different variables. So when we solve for the speed of a wave, we're going to still use distance, but in this case, the distance in a wave is called the wavelength. Thumbs up if you remember that. Thumbs up if you remember that. Oh, it's working? Maybe it was just lagging for a moment. All right. Yes, all right, so taking a look down here, you can see that the distance between a crest and a crest, or remember we talked about another way is to measure two bumps, a top bump and a bottom bump, that is your wavelength, right? So that is a distance, and it's gonna still be measured in meters. So we no longer call it distance when we talk about waves, we call it wavelength. Wavelength is the distance. And then down here you can see capital T. Capital T stands for period. You can see that in our chart over here. And period is still measured in seconds. It's the seconds that it takes for this one wavelength to occur, the time for that one wavelength. Let's go ahead and do an example because we know that whenever we do an example, equations make more sense. A single sound wave cycle travels 0.926 meters in 0.0027 seconds. What is its speed? In the chat box, everybody, please tell me, what is the units for meters? Sorry, that's not what I meant to ask. Meters is the unit for which variable? Take a look at our chart. Meters is the units for which variable? Is it speed, wavelength, or period? Oh, we love math. We do math together, so math is fun. Yeah, when we work on it together, when we annotate and work on it together, it's always more fun. Yeah, so taking a look here, remember meters is a distance, but for waves, the distance is called wavelength. So this right here is going to be our wavelength, and I'm going to go ahead and teach you, Mrs. Sepulveda mentioned it at the start of class, but the symbol for wavelength is the Greek letter lambda, which looks like an upside down Y or a weird looking H. Okay, taking a look over here, 0.0027 seconds. Seconds is the unit for what? Again, take a look at our chart at the bottom here. Yeah, you don't have to be good at Greek. It's just that we use a lot of the Greek letters in math and science because we run out of letters. We've just run out of Arabic letters, which are the letters that we currently use. All right, so again, seconds. Seconds is the unit for what? Take a look at our chart. Is it our speed, our wavelength, or our period? Pi is an excellent Greek letter. Yes, this will be our period, again represented by a capital T, also measured in seconds. So this is our capital T. Let's plug it in. So in for wavelength on top, I'm going to go ahead and put 0.926 meters. On the bottom, in for period, I'm going to go ahead and put 0.0027 seconds. Grab your calculators. Please do this math for me. What do we get? 0.926 divided by 0.0027. Make sure you're not giving me naked numbers. I need some clothes on those numbers. Give those numbers some units. Go, go, go. Let's put some clothes on them. Yes, the alphabet that you and I currently use is called the Arabic alphabet. So there's the Greek and there's the Greek alphabet and then the Arabic alphabet. All right, video is definitely lagging. All right, good. I see people beginning to type their answers. Jadelyn, I think that your decimals might have been off, so try that one more time. You're really close, but I think your decimal was off. Thank you. I see Brisa, I see Lisa, I see Caitlin. I see Angelo typing, Antoine working, and Greta working. Let's get some more participation. Ricardo, Matthew, haven't heard from you in a while. Madison, Lydia, make sure you're getting your answers in the chat box. Timothy, Rowan, and Kalia, want to hear from you. Awesome, getting more answers in the chat box. Great job, everybody. Yes. Don't be lazy with decimals. Yes, you should be getting 342.96 meters per second. And remember, that is actually really close to about 343 meters per second, which is the speed of sound in air. So we could probably theorize that this wave is traveling in air. Great job, everybody. All right, now we just learned how to calculate the speed of waves using period, but there's actually another way for us to calculate the speed of sound, and that's with frequency, because we learned an equation the other day where frequency is the inverse or opposite of period. So it's the inverse or opposite of period. So frequency equals 1 over period. So let's go ahead and actually derive the newest equation here. So speed, again, is wavelength divided by period. Now we can actually separate and pull these two different things apart. So we can pull this apart and put wavelength on the left and period on the right. So we're going to keep the wavelength on the top and we're going to keep the period on the bottom. And then to fill in the rest of the equation, remember, all I need to put here are ones, and that'll make sure that it's still the same variable. Anything over 1, anything under 1 is still going to be itself. All right, go ahead in the chat box, give me a birthday cake if you understand how I split this apart. All right, this is still saying the same exact thing. I just split them apart so I can analyze each part by itself. Great job, everybody. Thank you. Oh, awesome. All right, so wavelength divided by 1 is still going to equal wavelength. So I'm just going to simplify that down here to lambda. That's still going to equal lambda. Yeah, my daughter's 3rd birthday is today, and I am planning on making some chocolate tres leches cake for her tonight. So, and now I'm even hungrier. Why did I just say that? Yes, I'm excited. All right, so taking a look here now, this 1 over period, does that look familiar to you? Go ahead, tell me in the chat box. 1 over period is equal to what? 1 over period is equal to what? Take a look at we learned the other day. Thanks, Rishane. Thank you, Harmony. Yes. Yes, I will let her know. All right, in the chat box, 1 over period, this part right here, we learned what that equals the other day. What does that equal? Everybody, in the chat box, what does that equal? 1 over the period is the same as what? Is the same as what? What's on the other side of the equal sign? Excellent. I see Lisa working. I see Jade Lynn, Andres working, Rishane working. Let's get some more answers from Madison and Ricardo. Madison, Ricardo, haven't heard from you. Lydia, Matthew. Haley, Eric, Bryant, Annabelle, Alec. Again, 1 over period is the same as what? This part right here that we're analyzing, 1 over period is the same as what? Take a look at the other side of the equation. It's on the board. I'm pointing to it. It's on the board. I'm pointing to it. Tell me in the chat box. Yeah, it's the same as frequency. 1 over period is literally the equation that we learned for frequency. So instead of putting 1 over period, I can actually just substitute it with frequency. In the chat box, please give me a cup of coffee if that makes sense. Cup of coffee if that makes sense. So since we know the equation 1 over t equals frequency, instead of putting 1 over t, I can just put frequency. So this is the other equation. Different scenarios will require you to use them differently. All right, so in the chat box, 400 hertz. Hertz is the unit for what? We have a 400 hertz sound wave that has a wavelength of 0.9 meters. What is its speed? We're going to use our newest equation. Hertz is the unit for what? Hertz is the unit for what? Is it going to be the speed, the wavelength, or the frequency? This is one that we should already know from previous classes. We should be pretty familiar with this one. We think hertz, we think what? So remember, speed is like in a car, miles per hour. So the science version is meters per second. Yeah, remember, hertz is frequency. Frequency, hertz, yes. So this is going to be our frequency, or our F. So I'll plug that in down here for frequency. And what about 0.9 meters? If you read the question, it actually tells you what 0.9 meters is. 0.9 meters, is that the speed or the wavelength? Those are the two options we have left. We're annotating together to make it easier to solve the equation. Remember, annotation is key to doing well on equations. Yeah, this is going to be our wavelength, or remember our unit for, or our symbol for that is lambda. So down here underneath lambda, I'm going to fill in 0.9 meters. Multiply those together and tell me, what do you get? Oh my goodness, Brisa with the lightning fingers. Oh my goodness. Working so fast. 0.9 times 400, what do we get? And don't forget those units. Again, it's still solving for speed. This is just a different way to solve for speed. Lovely. I see Sally. I see Andres, Lisa, Jade Lynn, Antoine. Yeah, y'all are so fast. Great. Great job, Annabelle. Thank you for participating. I see Caitlin. Yes, it's going to be 360 meters per second. Great job. All right, let's go ahead and do a couple more practice ones just so that we're really confident with how to solve for speed.
Right here, we're going to look at waves in a lake are 8 meters apart, and I'm going to go ahead and just kind of highlight that, and pass a raft every 3.2 seconds. So what is the speed of the wave? So I'm going to go ahead and find the speed of V. So looking at this 8 meters, what am I going to be talking about here? Am I going to be talking about period, or am I going to talk about wavelength? What am I talking about here? Good. Region A's got an answer in the chat box. Excellent. Lisa's got an answer. Beautiful job. Yes, I'm going to be talking about wavelength. And remember, wavelength has that what I call like a funny H, but it is really called a lambda. So yes, that is going to be our wavelength. Now looking out here, 3.2 seconds. What do we have left over? What am I talking about here? What does that capital T mean? Does someone remember that? What does that capital T mean? Good. Antoine's got an answer. Sally's got an answer. Beautiful. Region A, beautiful. Yes, yes, yes. Lisa's got an answer. Beautiful. Yes, I'm going to be talking about the period. So remember, a period is going to equal that capital T, not the lowercase t. It is a period of time, not time itself. So let's go ahead and plug these numbers in. Obviously, we're going to go ahead and plug in 8 meters. And then we're going to plug in my T right here at 3.2 seconds. So once I have that, I go ahead and multiply that, or not multiply, excuse me, divide that. 8 goes into 3.2. How many times? Give me some answers up in the chat box. What do I get? Breeze. Oh, man, Breeze is so fast today. Sally's getting that. Yes, excellent. Yes, and I love the units too, Mrs. Larkin. This is awesome. Period 3 is on fire today. Caitlin, beautiful. Annabelle, awesome. Yes, I will agree at 2.5 meters per second. Beautiful job, everybody. So now let's take a look at the next problem. Let's annotate it together. A 110 hertz wave, and I'm going to go ahead and just highlight that wave along a guitar string, has a wavelength of 0.65 meters. What is the speed of the wavelength? So obviously looking back up here at 110 hertz, what am I talking about? Am I talking about frequency or wavelength? Frequency or wavelength? Lisa's got an answer popped up there. Good. Good, Sally. Region A, absolutely agree with all of you. It is going to be my frequency. My dead giveaway that it's going to be frequency is literally the unit hertz. When you're talking about hertz, you're talking about frequency. So let's go ahead and look at 0.65 meters. Obviously, it states it into our problem here. What am I talking about? Finish annotating? Yes. Beautiful. Caitlin's got an answer. It says it right into our problem here. You get so excited. I know it doesn't. Yep, I know. Yeah, we're talking about wavelength, okay? And if you read our problem carefully, it says it right there next to it. Wavelength. Beautiful. So let's go ahead and plug in our numbers. Obviously, our wavelength is going to be 0.65 meters. Our frequency is going to be 110 hertz, capital H, lowercase z. And so now we have a simple multiplication problem. What do I get? Daniel, I know you're like flash and you're like lightning here, but what do I get here? Good. Breesa's got it. Beautiful. Excellent. And again, love the units. People, you're putting clothes on your numbers. Love it. We don't want no naked numbers. That's gross. All right, here we go. 71.5 meters per second for the speed on this one. So this is in our slide 16. I want you to go ahead and take a look. Flip into your slide 16 on your own project, and I'm going to go ahead and show you right up here on the board. So looking at the top problem, don't worry about the bottom two, looking at the top problem here, the 110 hertz wave along a guitar string has a wavelength of 0.65 meters. What is its speed? I want you to go ahead and plug in the numbers. We already just did this problem. Remember to plug in 0.65 under wavelength and frequency 110, and then you're going to go ahead and put your answer as 71.5. We're going to put 25 seconds up on the clock here. Once you've done that, give us a green check. 25 seconds. Here you go. Go, go, go. Work, work, work. Absolutely, that would be super fast. All right, again, give us green checks if you're taking a picture. If you are doing pen or paper, if you're doing screenshots, just a green check letting us know you're still with us. Again, we have 31 of us in class. I'm seeing 15 green checks. I need to see more green checks to move on. Daniel, I have never seen that movie. I think I need to bring it up for my kids. I have never seen it on Disney. All right, here we go. Checking in with a few people. Alec, green checks, please. Looking for a green check from Daniel, green check. All right, I know you're in the chat box. Give us a green check to let us know. Eric, green check. Thank you, Daniel. Harmony, green check. Looking for a green check from Kalia, green check. Looking for a green check from Madison, Matthew, Ricardo, green check. Haven't heard from you in a while. And Timothy, give us a green check. Alrighty, let's go ahead. We'll go ahead and start moving people into the check-in room. Again, this room is just to regroup, and if when you're ready, come on back. We're more than welcome to have you. Alrighty, let's go ahead and move on. So looking at these problems, we're going to practice now a couple of problem solving with other variables, looking at other variables. I can't even speak right now. So let's read our first problem. Let's annotate it together. The speed of sound in an air is about 343 meters per second. What is the wavelength of sound waves produced by a guitar string vibrating at 147 hertz? All right, so what we're trying to figure out, obviously, is from the problem is our wavelength. So we have some numbers here. Let's go ahead and annotate those numbers. Looking at 343 meters per second, am I looking at speed? Am I looking at frequency? Who can tell me in the chat box? Good. I see an answer from Lisa. I see an answer from Caitlin. Absolutely. Remember what meters per second means. All these units kind of help us to realize what we're doing. I do need to see a couple more. Beautiful, Eric. See that? Excellent, Jalen. Here we go. We're talking about speed here. Beautiful. Looking at 147 hertz. Well, looking at the units, am I talking about, what am I talking about here? Good. Lisa's got it. Beautiful. Hertz is what? Good. Andres has got it. Oh my goodness, beautiful. If I know how to spell it, there you go. So knowing what we have known, so let's go ahead and plug in our numbers. We know what our speed is, our 343, not 0.3, 343 meters per second. Looking at our frequency here, we're going to go ahead and plug in 147 hertz, capital H, lowercase z. Now, we want to get that lambda or that wavelength by itself. So if I want to get that variable by itself, who remembers what we need to do? What do we need to do? Who remembers? Good, Lisa. Excellent. Excellent. Yes, we have got to divide. And so when we divide, we're going to go ahead and divide 147 hertz. And we need to hurry. 147, those go ahead and cancel each other out. We're going to go ahead and divide 147 on the other side because when you do it on one side, you have to do it on the other side. And what do I get? At 2 decimal places after that decimal mark, and it's going to be 2.33 meters. Beautiful. Let's go ahead and look at the next problem here. Sorry to move on so fast. Let's a hammer hits steel and makes a sound wave with a wavelength of 18 meters. Again, I'm going to take this number, 18 meters. If sound in steel moves at 5,940 meters per second, what is its frequency? So again, we are looking for frequency. If I'm looking at 18 meters, what am I dealing with? It says it right in the problem. What am I dealing with? Am I dealing with speed? 18 meters. What am I dealing with then, Antoine? Nope. We're dealing with a distance, but a wave distance. What do we call the distance in a wave? Good. Caitlin has it. Regene's got it. Beautiful. Wavelength. Beautiful. Let's go ahead and look at 5,940 meters per second, and that's going to be dealing with what? Meters per second. Beautiful. I see it up there. It is going to be dealing with speed. So let's plug it in here. So we're going to go ahead and put 5,940 meters per second, 5,940 meters per second. And we're going to put our wavelength at 18 meters. And so now, same thing. I have to get F by itself. So in order to do that, what I'm going to do is I'm going to go ahead and divide it by 18 meters. It's the opposite of multiplication. What I do to one side, I have to do the other side, so 18 meters. This has now become a simple division problem. Do the inverse, absolutely. So if it's become a simple division problem, divide 5,940 meters per second by 18. What do I get? Harmony's got an answer. Harmony, don't forget to get those clothes on that number. Excellent, Lisa. Yeah, there you go, Harmony. Good correction. Beautiful. Antoine's got it. I got 330 hertz is my frequency. This is in slide number 16. This is the bottom 2 answers. bottom two answers. Again, we've already done these answers, or we've already calculated this together. So you're just going to put in the numbers here. Remember to divide on both sides. That's the inverse. Green checks when you're finished. I'm only going to give you about 30 seconds to do this. 30 seconds for green checks. Go, go, go. Work quickly. Looking for a green check from Brian. Daniel, thank you, Daniel. I saw that green check fly up. Eric, Greta, green check. Looking for a green check from Ivana. Jaylin, good. Green check. Jose, thank you. Kalia, green check. Lydia, green check. All right, here we go.
Looking good. All right. It does look like Blackboard's giving every couple people some problems. So yeah, we'll just be patient. All right. So for the very last slide, slide 17, this is one that you'll be able to do on your own. So you need to choose a realistic frequency that can be produced by the voice or instrument in the song that you chose. So you can choose either any voice or instrument as long as it occurs in your song. So you can say I have a male voice, a female voice in my song. You can say there's a trumpet, a guitar, a piano in my song, etc., etc. Choose a frequency from this graph. The link to this graph is also in the slide already for you. So what you're going to do is, assuming that the speed of sound in air is 343 meters per second, you should be able to solve for wavelength. That's literally the same as what we just did right here, this question right here. The only caveat here is that you cannot choose 147 hertz. So don't choose 147 hertz because, again, that is the example problem that we did. Okay, please notice that right here in the graph, it might say 1K, 2K, 4K, 6K. K stands for 1,000. So if you see that, 6K means 6,000, or 6 with 3 zeros after it. I know, Sally, I'm so sorry. You always do so well, and yet Blackboard hates you so much. All right, so here's what the slide actually looks like for slide 17. So again, here's the question up here. Here's the link to that graph. Choose the voice or instrument and type right here what you choose. Tell me what frequency did you choose. Again, that frequency should be based on this chart, something that makes sense. If you want to choose an actual note that it produces in your song, that's totally fine, but that might take a little bit more research. Then go ahead and plug those things in. So we know the speed of sound here is 343. That goes in for our speed of sound. And we know that the frequency right here, our hertz, will go in for frequency, and we will divide by this frequency on both sides. So we'll divide by that frequency on both sides to get our final answer. All right, so again, that's exactly what we just did in example number 2 on slide 16. So if you need an example, go back to that example. Come to tutoring if you need to. We'll get a tutoring link out to you soon. All right, thank you. So that is just one that you need to complete before the end of the project, which will be due at the start of next week. All right, so for your attendance, I know that we are pretty much all done here. So let me go ahead and send out your links. Sorry for running over by a couple minutes. Go ahead and click on the link, click start a new thread. And today, all you need to answer is any answer from slide 16 of the Unit 4 project. This is to make sure that you are working with us on slide 16 of your Unit 4 project. So you can give us any of those 3 answers. Go ahead and do that, and we will start logging people out in about 60 seconds. Thank you so much. Thanks for working hard, and we will see you all later. Bye, everybody. Recording stop.